In this video, we're going to be talking about Dirichlet convolution. First, I want us to consider some more examples of arithmetic functions. So, at the very end of the last video, we ran into this function which I called e of n, which was defined to be 1 if n equals 1, and 0 else. For another function, I want to consider something I'm just going to call the 1 function, which is just going to be constantly equal to 1. Next, I want us to consider the identity function, which is just going to be equal to n. And it can be seen that well, these two functions in particular are completely multiplicative, but that doesn't really matter. All three of these functions are multiplicative. Actually, I guess the identity is multiplicative, I guess, too. But anyway, that's not really important. These are just going to be some sort of simple functions that we're going to use in this new exploration. So what Dirichlet convolution is an operation on the set of arithmetic functions. So if we take two arithmetic functions, f and g, we can sort of multiply them by taking the sum over divisors of n of f of d times g of n over d. So let's take an example. Really, this sum just depends on what n is, right? The divisor structure. So first, let's just take an example n value. Let's say 6. So this is going to be f of 1 times g of 6 plus f of 2, g of 3, plus f of 3, g of 2, plus f of 6, g of 1. Right? So we're just adding you take two pairs of opposite pairs of divisors of n, right? So they multiply together to n. And you take f on one value, g on the other, multiply that together, and then sum over all of those. And so it turns out that these three functions here are really helpful for understanding Dirichlet convolution. So for instance, as we explored in the last video, for sums over divisors, right? So this, a sum over divisors like this, is really just the Dirichlet convolution of f with the 1 function evaluated at n. So for instance, we saw in the last video that the sum over the divisors of n of phi of d was equal to n. And so, so what this means in terms of Dirichlet convolution is that we have phi convoluted with 1 equals I, right? Because this is the function that turns into n, and then here we're summing over just divisors of n of phi of d. For another example, we can consider let's say, let's consider the identity convoluted with 1. So this is the sum over divisors of n, and then the identity of d is just d, and then times 1, right? So just we're summing over the divisors of n. So this is the sum of the divisors of n, right? So we call that sigma of d, or sorry, sigma of n in the last video, or I guess 2 videos ago. Okay, so this is the definition of Dirichlet convolution. Now, it actually gives us some structure for arithmetic functions. In particular, Dirichlet convolution, which I'll just write as DC, together with addition, so I'll just write plus, makes the arithmetic functions into a ring. And if you haven't studied any algebra, a ring is just an algebraic structure which generalizes sort of multiplication and addition together on some set. In particular, this is going to be a commutative ring with unity. In other words, we have some identity, and I won't write 1, I guess. So the function e of n, which we defined up here, is going to be our identity for Dirichlet convolution. And in addition, so in addition, and not like the math addition, just in addition, the multiplicative functions form a subring. Alright, so let's see how this all comes together. So first, let's show that, that Dirichlet convolution is commutative, and this is, pretty easy because this sum is very obviously symmetrical, right? Sorry, this should be a D. I was thinking about 6. So in our example here, right, if we read it this direction, right, the numbers that f is being applied to go 1, 2, 3, 6, right? But if we read it in this direction, the numbers g is applied to is 1, 2, 3, 6, right? So there's this symmetry, and this is essentially what the Dirichlet convolution being commutative means, right? And essentially the way to formalize this is to say that d divides n if and only if n over d divides n. And then you can essentially use a substitution in this sum, saying, okay, I'm going to sum over n over d dividing n, so we get f of n over d, and then n divided by n over d is just going to be d, and this is g Dirichlet f. Alright, next we want to show that this Dirichlet convolution is associative. So in particular, if we take 2 arithmetic functions, we want to show that if we convolute f and g and then convolute h, it's the same as if we took f and convoluted it with the convolution of g and h. So if we write this down, right, here we have d sum over divisors of n, and then on the inside we're going to have a sum over the divisors of d, so I'll call that a dividing d, so f of a, g of d over a, and then this is multiplied by h over n over d. Now, if we take this term, and in fact, I'm going to write it sort of differently. I'm going to start, instead of starting with f of d, I'm just going to start with f of n over d, which is valid, right? Because it doesn't matter which way I do it. And then here I'm going to have the sum over the divisors of d of g of d over a times h of a. So again, this is convolution of g with h, and then this is f. So we want to show that these two things are equal to each other. And the way to see this, and in particular the reason why I wrote, there's some sort of choices I made in writing this, valid choices, of course. Here we have this common term of g of d over a. And this allows us to see that if we basically the numbers a, d over a, and n over d, right, we could see they all multiply to n. And these two, of course, multiply to d because they come from the convolution of f of g applied at d. So these numbers have to, of course, multiply to d. But essentially, these are, in terms of n, right, these are sort of independent. In other words, like this double sum is going to run over all triples of numbers that multiply to, all triples of positive integers that multiply to n. And so when we write it like this, we can just focus on d over a. And essentially, these two things are going to be independent of each other, right? So if we fix d over a, then we see that the other terms, f of n over d and h of a, and then here we have f of a and h of n over d. And so clearly what's happening there is that you have f convoluted with h applied at na over d, right? Because that's just the multiple of these two, which is, of course, just n over d over a, where d over a is the number that we were fixing. So this is a fixed number. If we fix d over a, so we're factoring out g of d over a from both sides because we have that common term, and then we see what's left over is f convoluted with h applied at n divided by d over a. So Dirichlet convolution is associative. Next, we want to show, again, a ring combines multiplication with addition. So one important thing that comes with that is that we have a distributive rule. And thankfully this one is not as complicated as the associativity. So here we just have f of d, and then on the inside here we're going to have g of n over d plus h of n over d. And here we just have like regular number multiplication, right? So we can distribute, and then of course the sum is going to distribute over this addition sign. So we have f of d, g of n over d, plus f of d, h of n over d. So, right, this these are obviously just straight definitions of f composed with g and f composed with h. Now we want to show, again, as I said, that E of n serves as an identity. So let's just consider f convoluted with E. This is going to be a sum over divisors of n, f of d, g of n over d. Sorry, not g, but e. E of n over d. And since E is going to be 0, it's only going to be non-zero when n over d is 1. So n over d equals 1 is the only time that we're going to have a non-zero term in this sum, right? In other words, d equals n, so this whole thing is just going to equal f of n, right? So here we should technically write this as being evaluated at n. This is going to be f of n times e of 1, right, which is just 1. So, and since we already established that this is commutative, right, so we would write like f star e is e star f, which is f, right, because that's typically how you express that something is an identity in the general case where there's non-commutativity. But since we have commutativity, we don't really have to worry about that. So this completes the statement that the arithmetic functions form a ring under addition and Dirichlet convolution. Now we also claim that the multiplicative functions form a subring, and all we really have to do for that is to show that if we take two multiplicative functions, then we need to show that their convolution is multiplicative. And so let's say we take two numbers, as always, two coprime numbers, x and y. So their GCD is 1. And so if we look at f star g applied at xy, we get a sum of divisors of xy of f of d times g of xy over d. Now, as we've argued over and over again, a divisor of xy, where x and y are coprime, is going to uniquely factor into a pair of divisors of x, of a divisor of x and a divisor of y. So d, we can replace d by d1 and d1 times d2, right? G of xy over d1, d2. And of course, since x and y are coprime, then d1 and d2 are going to be coprime, and x over d1 and y over d2 are going to be coprime. So this just means that we can, once we write the summation terms, we can split the functions given that f and g are multiplicative, as we are assuming. So we can split the functions like this, and now if we just pair up the d1 and d2 terms, right, the x and d1 and the y and d2 terms, since these two summation summation rules, I can't think of a better word to aptly describe them, but these two summation conditions, these two conditions are independent of each other, which means we can simply write this is a double sum. I should be writing a double sigma, but I'm kind of lazy. We can factor this double sum over two independent conditions as a product of the two sums. This is d2 dividing y, f of d2, g of y over d2. And of course, these two sums are just f composed g of x, and then f convoluted g of y. So f convolute g is multiplicative because we started with evaluating at x times y, and then we ended up with evaluated at x times evaluated at y. So this means that the multiplicative functions do in fact form a subring of the arithmetic functions. Now, one thing that rings can't do is division, right? Basically, division is, when you add in division, that's when you get a field. A field is when you have unique inverses of elements. But we will see in the next video that there is a way to perform a sort of inversion on arithmetic functions, and that is the Mobius inversion. So I hope to see you then.